Okay, so good news, you already know what a tangent vector is to the graph of a vector valued function. Why is that? So it's not a unit tangent vector, but you should already know how to get a tangent vector that's tangent to the line of motion. Mute yourself, folks. Okay? I'm going to open it up. You guys should know the answer. How do I get a tangent vector to the graph of a vector valued function?
Derivative.
Good. Thank you. It was the velocity vector, right? The first derivative. So it's r prime. You already know how to get a tangent vector to the curve. If you don't know this by the midterm next Monday, you're going to be hurting because that's like a key fact. Okay, so if you unitize it, which we haven't done yet, but if you do unitize it, then you're going to get something known as a unit tangent vector. So we're going to be doing that. So you already know that r prime is the tangent vector, provided it exists. And if you have a tangent line at a point P, then that line passes through the point P, and it's parallel to the vector valued function's derivative. So you can use that guy as the evaluated at the point, of course, as your direction vector. And we did an example like that Monday, and I hope you remember that. So you really need the r prime to not be the zero vector if you're going to have a decent tangent vector, because otherwise it's just a dot. It's not fun. Okay, so provided that your r prime isn't the zero vector, here is the definition of a unit tangent vector. All it is you take the velocity vector, the first derivative of your vector value function, and you unitize it, and you all know how to do that. So why do we need the condition that we don't want the vector valued function's derivative to be equal to the zero vector? Well, because we're dividing by the magnitude, and the zero vector's magnitude is what?
Zero.
Yeah, and we don't want division by zero because that would be bad. So that's why we're making that a condition. Okay. Now, sometimes getting the unit tangent vector can be somewhat messy, especially if you do a whole bunch of nasty derivative rules like quotient rule and a chain rule all at the same time and so on. And I think I put a problem or two in your homeworks so you could have fun with that. But I'll keep it kind of easy for the lecture purposes. Okay, so let's start with an easy example of getting the unit tangent vector. So here's a vector valued function right here. It's pretty easy. It's a two-dimensional one. They want us to get that. That's the same as get t of t. So big T, and I want you to get this notation. If I ask you to get big T, don't email me and go, I don't know what big T is. What's that? We just said what it is on the previous definition. Big T is basically the unitized velocity vector. That's what he is. That's the notation. So let's go get the derivative. And I'm going to use component form. So the derivative of t with respect to time t is 1. The derivative of t squared, 2t. So there's the velocity vector. And now you're going to unitize it. So we are going to need the magnitude. So let's go get that first. And so we're going to take the square root of the sum of the squares of these guys, and we get that. Now, here's a question for you, true or false? Can we simplify this a little bit and make it look prettier?
No.
Magnitude, is that legal? Yes or no?
No.
No.
So, that's illegal math. If I catch anybody in the class doing that, you're pretty much going to lose all the points on that whole problem for violating some basic math that you should learn back in an algebra course. So don't do that. This is as simplified as we get. So now your big T, which by definition is the unitized velocity vector, we're just going to put everything together now. And then we'll distribute this scalar function so that the unit vector, the unit tangent vector, is this. Now notice it is a function of t, that it is going to vary depending on what location we are on the curve itself, you know, what time it is essentially. So it is going to vary. So there we go. Now they did want us to evaluate this at time t equals 1 second. Okay, So at time t equals 1 second, you're just going to substitute t equals 1 into this thing, and you'll get a constant vector, easy peasy. And I get this vector here, 1 over square root of 5, 2 over square root of 5. And you don't have to rationalize your denominators in my class. I'm totally okay with this. I do want to say you should know how to rationalize any quotient that has a radical in the denominator, because sometimes I might give you a multiple choice MyMathLab problem, and sometimes of the choices they give you in the MyMathLab problem, all of them have a rationalized denominator, and you're like, oh crap, so your answer might be correct, but it might look like none of the choices match, and it just might mean you need to go one extra algebra step and you got one of the answers there. Okay, now for this picture, if you use your graphing calculator and you graph this vector valued function, it is a parabola. So there's the motion, that's the motion function. Now the vectors that we just figured out, this unit tangent vector here, you could draw it in standard position where it's just sprouting out of the origin, but they translated it so that it's sprouting out of the correct position that it corresponds to when time t is equal to 1 second. And please note, you want to do that because then you can tell that this thing is indeed a tangent vector to the graph. And that's important that you're able to tell that that is the case. Because let's say you did graph it and let's say it was all fakakta all over the place. Let's say you, just say by accident you did some sort of wrong math and algebra or arithmetic, and let's say you got -1 over square root of 5, 2 over square root of 5. I'm just giving you a possible setup for you got something wrong. How would you know that's not it? Well, this vector is pointing, if you graphed the point, -1 over square root of 5, 2 square root of 5 would be something like this. It's over here in quadrant 2, and then if you graphed it sticking out of the point that it corresponds to, you're like, oh, like this? Well, that's not tangent to your line of motion, so that you did something wrong there. It's like, oops, that's not working. So you have to be careful when you're doing these. Okay, now example 2. We're going to find a general formula for a unit tangent vector. We're just doing it again, but this example is a little more high powered than the last example because it's in 3D instead of 2D. That's the only difference. Okay, we're doing the same stuff. Nothing major. So how do you get big T, which is what they're asking us to get? The unit tangent vector, you do the same as you did before. You get your derivative of your vector valued function, the motion function essentially, your position function. And the derivative of cos is minus sine, and then the middle term's derivative is 2 cos, and then the last derivative of t is 1. You are going to need to go get the magnitude, so when you put it all together, okay. Now, is this totally simplified or not?
No.
Adriana, to answer your question, can you do 1 plus 2 absolute value of t when we were talking about distributing a radical? No, it's illegal math to distribute a radical. I still don't think you really believe me. So I think I'm going to do a side note, and this is for Adriana over here, Adriana. Listen closely, Adriana, I'm talking to you, girl. Is it true that the square root of 4 plus 9 is equal to the square root of 4 plus the square root of 9? True or false?
False.
Is the square root of 13 equal to 2 plus 3? Yes or no? Adriana, you tell me. I'll look in the chat box for you. False, thank you. So please don't ever even think about distributing a radical over a sum or a difference. Now you are allowed to do it over a product. Like if you were doing, if I changed this problem altogether and said, hey, the square root of 4 times 9, that's a different problem. Is that equal to the square root of 4 times the square root of 9. True or false? True or false?
True. It's true.
It's true. So if you have a multiply and you're taking a square root of a product, it's certainly legal to rewrite it as the product of square roots or whatever the radical is. But you can't do it for sums or differences. So don't even try doing it. If you ever do it in my class, we're going to have a little conversation. It's not cool. One thing you'll learn about in calculus is you will learn your algebra. There's an old cliche, and if you haven't heard it, you heard it here first. If you really want to see if you know your algebra or not, take calculus. Because in order to be good at calculus, your algebra skills have to be strong. Okay? And you probably found that out in a Calc 1 class somehow. At least when I teach Calc 1, I notice one of the reasons why a lot of students fail it is their algebra skills are weak. It's not the calculus that's hard, it's that they can't factor polynomials, they can't figure out the lowest common denominator of fractions, they don't know their exponent laws, they do silly stuff like trying to distribute a radical over a sum, like over and over and over repeatedly, even though I tell them, please don't do that, and then they still do it. I'm like, what are you doing? So is this simplified completely, yes or no? Back to the problem at hand.
No.
Or can I simplify it further? No. What else can we do?
You can
Pythagorean theorem?
do that.
Well, I think it's a trig identity.
I think since square plus cos square equal 1.
Mm-hmm. And then what is this simplified to?
Simple.
Square root of
Mhm.
5.
Square root of 5, yeah. And now you're ready to put it all together. Your unit tangent vector is going to be r prime all over the magnitude of r prime. And then please distribute your scalar, otherwise I'll dock you points. I want to see you finish it out. And then they did ask us to evaluate this guy when time t is equal to pi/4 seconds. I always think of t as being seconds, although it doesn't have to. Could represent anything, you know. But if I'm going to evaluate at pi/4, then I'm going to get a constant vector. So what's the constant vector? Well, shoot, man, what is the square root of sine and cosine? Or excuse me, what is sine and cosine evaluated at pi/4? Anybody remember?
Radical 2 over 2.
Radical 2 over 2, yeah. And so if I clean this up, so, you know, I'll do this in slow motion. It's like, okay, square root of 2 over 2 all over square root of 5. And then this is 2 times square root of 2 over 2 all over square root of 5. Now clean this up, because even though I'm okay with you not needing to rationalize denominators, I don't like complex fractions where you have a fraction inside of a fraction. That's yucky. So go the extra step and rewrite it. And after reducing to lowest terms, you'll get this vector here. And I'm done. So there's the problem. Now they did give you a visual on this, which is kind of cool. The visual here is they graphed this curve, this 3D curve, which happens to be a helix, which is kind of cool. If you're into biology, that's kind of neat. Because helix, if you look in 3D, they kind of look like a spring, like woo, like that. That's kind of cool. And so the point at which time t was equal to pi/4 gives us a position here on the curve right there at square root of 2 pi/4, that you would just find that by plugging in t equals pi/4 into the position function. And then the tangent line to that, you could draw a tangent line, and as somebody said, which they didn't, but let's just say they did, go, oh, what are the parametric equations for that tangent line? Do you know how you would finish out this problem? I'll open it up for chat.
You need the vector, the direction vector, which in this case is a unit tangent, or the
Yeah, you can
tangent
use
vector.
the unit tangent vector as your direction vector. Very good, George. Very good. You got it. Yeah, you could definitely use that guy as your direction vector, so he could serve as your direction vector. Certainly, that would be legit. And you have a point on the curve right there because you plugged in time t equals pi force into your original position function. And that gives you enough info to get your parametric equations for that tangent line, wouldn't it? Like if I put this on the midterm, would you be able to do it?
Yes.
Right now, since we're only 5 days away from the midterm, you know, everything's fair game. Like be thinking every time we look at a problem, is that midterm material? Yeah. Okay, now let's talk about the principal unit normal vector next. New topic. Okay, let's go to example 2, the two-dimensional, the 3 example. Let's talk about that guy. In this example here, we know that the unit tangent vector, I didn't draw him, but if I did draw him, he would be a little tiny unit vector that would be tangent to the line of motion. So there he is right there. And you can draw him at various locations. Like if I drew the unit tangent vector all through this curve, he would just keep always being tangent to the curve no matter where you draw him. Okay, fine. Now, what if you wanted to get a vector that's orthogonal to these big T's? Well, I hope that you can appreciate in 3D, there's infinity vectors that could be orthogonal. I could get an orthogonal vector would be pointing up, but what about pointing out? What about pointing down? There's all sorts of possibilities. There's infinity possibilities of a vector that would be orthogonal to big T. But I don't want infinity choices. I want to narrow it down to a single choice. How do I do that? And so I'm going to give you the thinking on how the physics folks pick the one. The one. So we want the one. It turns out big T, his derivative, which also is a vector, is the orthogonal guy we want. Okay, now let me give you the proof of why that's the guy who's going to help us out. Do you recall this theorem? It says if the dot product of a vector with itself is a constant, a scalar, which doesn't always happen. Sometimes vector valued functions are functions of t. But if it is a constant, then r dot product with r prime is equal to 0. And I already proved this for you because I took the derivative of both sides and we used the product rule and everything. So this is a fact. So check out us using this handy fact in the following. Well, what happens when we take the unit tangent vector and dot product him with himself? What is that equal to? Now, here's another thing I want you to recall before you do this. Do you remember if you take the dot product of a vector with itself, it gives you the same result as the magnitude of the vector squared? Does anybody remember this theorem?
Yes.
I also
Yes.
proved that for you. Okay, so I'm saying that the dot product of the unit tangent vector with himself will give you the same result as his magnitude squared. But wait a minute, by definition, what is the magnitude of the unit, that's a big hint, the unit tangent vector?
Uno.
Yeah, and that's a constant. So this means that by this theorem up here, I'll put another star by it, that the unit tangent vector and his derivative give you a dot product of 0, which means they're orthogonal. Now, what we're going to do is we're going to unitize big T prime. So by normalizing, which in this case is going to mean the same as unitizing, by unitizing big T prime, you obtain a very special vector called the principal unit normal, and this is where normal means orthogonal, vector. And now we're going to get the definition of this principal unit normal vector. Here it is. And the notation we use for him is big N. And all you do is you get big T prime and unitize it. That's it. And assume, of course, that big T prime is a 0 vector because you don't want to divide by 0. Okay, now it's sometimes really a pain to get this. This can be a pain to get just because it takes a lot of algebra. Lots of calculus, possibly, sometimes in the algebra put together, and it can be a major pain in the buttocks. But If it's a 2D problem, you might be able to quickly get the big N without having to do much work. Here's the way you cheat. Okay, how do you cheat to get your big N? In 2D, we know that big T is a vector that's tangent to the curve. So in 2 dimensions, there's only 2 possibilities for a vector to be perpendicular to that vector that's in blue there. I could either have this vector, there's a 90-degree angle, or this vector that they're showing here. So I have only 2 choices. So the 2 choices, and this is the cheating way to get big N, okay? You can only do this in 2 dimensions. 3 dimensions, it won't work. But in 2 dimensions, you, and remember, you just want this guy, when you dot product it with big N, to give you 0. So you could have him have negative Y and then positive X, and you can check that when you dot product these 2 guys together, you will in fact get 0. Or your big N could be positive Y of t, negative X of t. So it's like you swap the 2 components and negativize one of them. So which one is it? Because you don't just get to pick your favorite. Well, I like this guy the best. No. It ends up being the one that's pointing in the direction that the curve is turning. So it's on the concave side of the curve. It's pointing in the direction that the curve is turning. Okay, that's how you pick the right one. So in this case here, it ended up being the one that was this one here, I believe. Okay, so this one turned out to be the right one. Okay, now in space or 3D, you can't use that little trick, sorry. You have to do all the hard work. But it's still going to point in the direction that the curve is turning. That never changes. So in this cute little curve here in 3D, big T is always pointing tangent to the line of motion, and big N will be orthogonal. So keep that in mind. Now let's talk about big B. So in physics, there's this thing called the T and B frame. You may have heard of it if you studied motion in a physics class. And so the T, we already know what that stands for, unit tangent vector. Big N, you now know it's an orthogonal vector to T, and it's the principal unit normal vector. Fine. And the way you get it is you find big T, take his derivative, and unitize it. But then what about this B guy? What's this B? The B. So the B stands for binormal. It sounds almost like some sort of psychological disorder. But anyway, the binormal vector is defined to be the cross product of the unit tangent and a principal normal vector. So that's kind of cool because you guys know about cross product. Yes, indeed. So in general, the vectors T and B starting at various points in a curve, they form this set of orthogonal vectors. I already told you what it is. It's called the T and B frame. And the T and B frame, it plays an important role in the branch of mathematics known as differential geometry. So if you take a differential geometry class at UCSD, you're probably going to get into this. Also, if you are an aerospace engineer, you're going to need to know about your T and B, because when any whether it's an airplane or a missile or whatever it is you're working on in aerospace, as the airplane or missile moves through space, you want to follow its T and B frame as it moves all over the place. So this is important. And I remember when I was in aerospace, we also had to be not only think of T and B, you had to think of pitch and yaw, because as your plane is going on some line of motion, it can kind of tilt to the left or the right, or forward and back. So you got pitch and yaw, and if you had a circuit that you were building or some piece of equipment that had to go into the vehicle and it couldn't handle pitching or yawing, and it would shut down, then you did not have your circuit to what they call military specs, mil specs, and you had to go start over and figure out how to do that. Okay, so knowing what we just learned, let's go find N and B for the curve in example 2 that we already did. Okay, so we already got T, so I hope I'm not going to get it all over again. We got that T was this vector here. Okay, n, we need to go get n, because I don't think we got n. Or did we get n? I don't think we got it yet. We just talked about it. So we got to go get n because we didn't get it yet. Okay, and yes, you're going to be doing this not on midterm 1, but midterm 2. So n is, by definition, the derivative of the unit tangent vector getting unitized. So we need to get this first. So how do you get that? Well, you already got big T, because we did that already when we did example 2. So just go get his derivative. And this is an easy one to get. Usually big N can be a pain. But this one's easy because you're just taking derivatives of sines and cosines, and it's pretty easy. So the derivative of negative 2 over square root of 5 sine is negative 2 over square root of 5 cos. And the middle component, I think the derivative of cos is negative sine, so you've got to put a negative in there. And the derivative of a constant is 0. Fine. And since you're going to unitize it, I might as well go ahead and get that magnitude. And, you know, 0 squared is just 0, right? So you're going, all right, so what do I have here? Well, I'm going to have 4/5 cos squared of t plus 4/5 sine squared of t. And you can simplify that further, because if you factor out the 4/5, you get cos squared plus sine squared. I hope we all know that's 1. And then I want you to clean this up a little bit, because this is a radical of a quotient, and there is a radical law that allows you to rewrite a radical of a quotient by taking the quotient of the radical. So it's that. And now you're ready to put it all together. So big N is just big T prime over the magnitude of big T prime. So you're going to go, okay, I got this. Oops, sorry, cos. I'm just trying to go real fast here because I want to get through this week's material, and it's good times, good times. Now, dividing by a fraction, you know, multiply by the reciprocal, and then after reducing to lowest terms, you're simply going to have this easy peasy, oops, I forgot my negative, big N. So here is the principal unit normal vector. Fantastic. So how do you get the binormal vector? Big B. Take the cross product of T and N. Now, let's talk about cross product, because on a quiz, not this last one, but it was last week's quiz, I had to dock some of you a point, and I'm going to dock you more points unless you're cleaning up your act here. When you're doing the 3x3 determinant method, which is pretty much the only way I want to see you do your cross product, okay? I want to see the setup. You have to put these vertical bars here. That's not absolute value, okay? When you take a linear algebra class, you'll get, this is how you denote taking the determinant of a matrix. And across the top row, I want to see I hat, j hat, and k hat. If I don't, this is what some of you did. You kind of put your bars like they were cheesy bars that were not strong. And then you put your I hat, j hat, k hat above the bars. I'm going to take away points. Your I hat, j hat, k hat have to go inside of those bars. They're part of the determinant. And yes, it matters. Like, well, you're just being a stickler. And yeah, because if you're going to be an engineer, or you're going to be a mathematician, or you're going to be a scientist, or all of the above, you care about detail. And if you're not the kind of person that cares about detail, you may want to consider majoring in business or marketing instead. Just a thought. Okay, now, to do the cross product, you know, you're going to have a 2x2 times I hat minus a 2x2 times j hat plus a 2x2 times k hat. This is a good review for the midterm, because you're going to do cross products on the midterm for realsies, like in more than one location. So when you do this, the I hat is going to end up having, you know, 2 over square root of 5 cos, 1 over square root of 5 minus sine t 0. This one's going to have minus 2 over square root of 5 sine, 1 over square root of 5 minus cos 0. And this one's going to have minus 2 over square root of 5 sine, 2 over square root of 5 cos minus sine. And then you have to do these products. So the major diagonal there, you're multiplying by 0. Well, anything times 0 is 0. Okay, fine. So you're going to go 0, and then minus, and that product is a negative, but minus a minus will give me a positive. Sine t over square root of 5, I hat, minus, and then when I do the major diagonal again, I get a 0, a minus, and it looks like minus a minus again, so I'm going to have a plus again. cos t over square root of 5 j hat plus, and ooh, this is going to be a mess. A negative times a negative is going to give me a positive 2 over square root of 5 sine squared minus, and then this is going to be a negative, so a minus is a plus. Okay, and then you can clean this up. Okay, so I'm going to end up getting, I'll put this final answer in component form. My big B, remember this is big B we're getting here. He's going to look like, what is he going to look like? Oh, sine t over square root of 5 for his first component minus cos over square root of 5. And then after simplifying the last component using a trig identity like that. Okay. Now, folks, if t and n are like doing that, and you use the right-hand rule, remember the right-hand rule? Where you curve your fingers through the vector t first, then n, and then look at where your thumb is pointing. So all three of these vectors are orthogonal to each other at any given point in time, okay? Now at the point P, which they gave us is when t equals 0, this is what we're finding here, the R evaluated at 0, so the position of the object as it's moving will be located at, 0, 0, 0. So that's a position. Okay. Excuse me, 2. Because cosine of 0 is not 0, it's a 1. So there's your position, okay, or a point what? We want to find the equation of a plane that contains both the vectors t and n. So here's your plane. I'm just drawing a picture here. And you know that they're telling you that t and n they live in the plane somewhere. And of course they're orthogonal, so I just draw them like this. And then now we have a point P in the plane, this point 2, 0, 0. Do you have enough information to get the equation for this plane, knowing what you know about equations for planes? This right here is a point on the plane. Do you guys remember this formula? Maybe I have to put it up here. This is good review for the midterm, because you bet your sweet bippy you're going to have midterm questions asking you for equations of planes. Okay? Do you have enough information to give the standard equation for the plane? Okay, who wants to get an A on that midterm, huh?
Can you remind me what information we have currently?
Yeah, I sure can. You have two vectors that you know are contained in the plane. And we also have a point in the plane when time t equals 0.
Mm. So we have
an equation that has these guys and this guy. Does that
cross
help?
product.
Okay, but we did that already, right?
Yeah. So you would have to use,
So we probably, this guy here is going to be your normal vector to the plane, although you do want to evaluate it at the point when time t equals 0. So this is a normal vector to the plane because of the fact that it's a cross product, right? So the B, if you evaluate him at the time when t equals 0, you'll get the constant vector we'll use as the normal vector. So sine of 0 over square root of 5, negative cos 0 over square root of 5, 2 over square root of 5. That's going to be our normal vector. So I get 0, negative 1 over square root of 5, 2 over square root of 5. And folks, that's going to be the A, B, and C in my equation for the plane. Here's A, here's B, here's C. If right now you're either A, falling asleep, or B, I don't care, let me remind you that this is exactly the kind of things that I test on a midterm. Like I try to see if you know what you're doing. Not just, oh, well, I saw a problem like it, so I only understand problems that I kind of sort of already did. If you're that kind of student, then you might get a B or a C, but probably not the A. So You may want to start making connections in your brain of what all this stuff has to do with each other, because that's the sign of an amazing student, when they try to really get it. Not just, oh, you know, I'll sort of kind of get it and hope for the best. Well, could happen. So what about the x naught, y naught, and z naught? What goes there for the equation of the plane?
Zero.
Your point on the plane?
The point on
Yeah,
the
so
plane.
what's
Two
my,
zero.
here's the point on the plane.
2,0,0.
Yes, that actually, that position is going to give me the point on the plane. So there's your x naught, your y naught, and your z naught. So when I start substituting all these things into my equation for the plane, you know, the a is 0 here, so that kills off that first term. Okay, fine. Then I'm going to have negative. Oh, by the way, I can use any vector that's a multiple of this, because, you know, multiples count as normal vectors too. If I multiply this by square root of 5 just to kill off fractions because they bother me, then I can use just as good. And if you want, you can keep the denominator of square root of 5. It's just that your equation for your plane is going to look kind of ugly. That's all, because it's going to have all these yucky fractions in it. But I'll have negative 1 times y minus the y coordinate of my point. Oh, that's 0. Plus 2 times z minus, oh, that's 0. Okay, fine. And if I clean this up a little bit, I'm going to get negative y plus 2z equals 0. And I'm done. That's the equation of the plane that contains both vectors, the unit tangent vector, the unit normal vector, at the point when time t equals 0. Now, for you physics buffs, I'm talking to you right now. You physics folks call this, you have a special name for this plane, okay? It's called the osculating plane, okay? I don't make this stuff up. I just report it, okay? The osculating plane. All right. We're officially done talking about unit tangent vector and unit normal vector. But what do they have to do with anything? Like, who cares? Oh, whatever, you get a vector, you unitize it, big whoop. They're going to come up a lot in this course. So one application for these is going to come up in the next section here. Actually, 2 applications, one for arc length and one for curvature. So those are going to be some applications. But I want to caution you, because I think I've mentioned in this course, at least the other day, the screen sharing is lagging. I don't know what to tell you, Vanessa. I can't fix it, okay? So there's nothing I can do. So it might be on your end, might be an internet problem. Sorry. Internet and learning remote is tough. Always a challenge. So we're going to learn about arc length and curvature in the future when we go into learning about, so let me go back to here. Remember I told you there's 4 big boxes for this course? And good news, you already finished the first box on fun and play with vectors. And we are currently doing the second box of stuff, vector valued functions, where you're learning about big T and big N and B. That's fine. But what's next for you? Well, the next box we're going to get into, we're going to start next week. And we're going to start the multivariable calculus portion of this course. And so it's going to seem like a lot of these vector valued functions go away for a while. It's like, wow, what do we spend like a couple weeks studying all that junk for? Because they don't come into the conversation until a little bit later, after you get some of the basics of multivariable calculus down. But they're coming back. So it's all going to come together eventually. So you don't want to just learn one thing and go, oh, it doesn't seem like we really care about that. We're done. It'll come back. So T and N, yes. Oh my goodness. Especially when we get into vector calculus and start doing flux. Okay. So let's do arc length first. Good news. You already learned this in Calc 2. Really? Yeah. Believe it or not, in Calc 2, you saw this. And if you forgot, I'm here to remind you. In Calc 2, when you studied parametric equations, one of the calculus ideas from the parametric equations, if you were given a curve described by parametric equations, you can find its arc length. And you were given this arc length formula. Now, it only works for 2D because you only studied parametric equations in 2D when you did Calc 2. But we can jack it up to 3D also. It works in 2D as well as 3D. Well, what do you mean? Well, if you have a curve that has 3 parametric equations, which you can just jam into a vector valued function and use the parametric equations as its components, same thing. And you've got some interval A to B, and you need smoothness, otherwise this Arclength formula won't work. So what does it mean to be smooth? Make sure I tell you this. It must not have any sharp corners, so no sharp corners or cusps in the interval. So what I'm saying is, let's say your curve goes like this, woo, woo, all these weird cusps. This, and let's say time t equals A is here, and let's say time t equals B is way over here. You would not be able to use this formula to find the arc length from here to here, because you've got a cusp in between that interval. It won't work. You can use it, and you'll probably get something funky like 0. It's like, what? That arc length isn't 0? So if you have that, or somebody tries to fool you and make you do that, this arc length formula can be used, but what you want to do is figure out the time at which it has that sharp corner or cusp, and then find this arc length going up to the cusp, and then add it to the other arc length going from the cusp to your other time. Then you can sum the results and you're good. Okay, now I want you to get that when you learn this Calc 2 formula, what were you really doing? You were basically integrating from A to B the magnitude of the velocity vector, which has another name. It's called speed. That's basically what arc length is. All it is, all arc length is you integrate speed. And so this right here, which is the 3D version of arc length, is just the integral of speed. So that's good to know. So let's do an arc length problem in 3D. Okay, and then I'll do another one that's a challenge, okay? Now, as far as the quiz 3, as you know, I don't give out solutions because you can go into my math lab and do some review or go look at the corresponding homework problems. But if you're interested in talking about, you know, the solution, like maybe you neglected to show me intermediate steps, or your notation was a little off and you're still confused and not clear of what is needed to get all your points, I would again encourage you to come to my office hours, and I'd be happy to do any solution or solutions on that quiz that you'd want to look at, okay? But you got to show up. If you don't want to show up, then you can go to tutoring, you know, that's always another option. Okay, find the arc length of this curve. It's 3D. Yeah, I know, no problem. So first you want to find the speed. Well, how do you find speed? Well, first you got to get the velocity vector, because speed is the magnitude of velocity vector. So you're going to take a derivative of this. I'm going to go pretty quick. Derivative of 2t is 2. The derivative of 3 sine 2t is 6 cos 2t. And then the derivative of 3 cos is negative 6 sine 2t. Fine. And then the speed is going to be this big old radical. Oh my goodness. The hard part about these arc length integrals is after you set it up, it might not be integrable. So you may have to whip out your calculator and use your one of the menu items that does definite integrals for you. And that, sometimes that happens. So here I'm going to have the sum of the squares of the components. And you always want to make sure you simplify completely, because I think I'm going to use another one of those. Sorry. I have one of these, I don't know if you guys are nerds, but have you guys ever heard of one of these cooling stands that you can put your laptop on that has these little fans? Well, I got one of those, right, for like 30, 40 bucks. And it's supposed to, you know, you lie your laptop on, it's supposed to cool it off. It doesn't really work that well. I still get where my laptop gets hot, and what happens when a CPU gets hot, for you computer nerds, is it slows down. And it's a real pain, because when I'm writing here on my tablet or my Surface, even though I'm writing super fast, this thing is like lagging really slow. So Vanessa, it could be because, you know, my computer sucks. You know, yeah, I spent all this money on this great Microsoft Surface Pro, and it's a piece of crap. I hate it. If anybody has any recommendations for a better laptop, I'm willing to pay the money, but somebody tell me it's something that doesn't get hot, doesn't have these lag problems, you know, and also has better features than this crappy Microsoft. I'm not a big fan of Microsoft. So Adriana, Microsoft heats up a lot. Yeah, it does a lot more than my ThinkPad ever did. My ThinkPad would get a little warm, bag of ice and a rubber band. Okay. David, that reminds me of a funny story, which I'll tell you right now because we need some comedy relief. Back when I was a digital engineer, I did a lot of circuit design back in the old days when I was in aerospace. And back in those days, you know, having memory was a big deal. Like now you can get a memory chip for like pennies. You know, I could get a gig for like nothing. But back then, they were just starting to make chips that had memory. So we got lucky. I was in research and development, so they had a few dollars. So we were all excited. We bought this huge chip, woo, that had like 1 kilobyte of memory on it. Oh, wow, that's a lot. Not in today's, you know, that's old fashioned. But back then it was like, oh my God, we got all this memory on our board. Let's go test it out. Well, it ran hot. So we had a can of Freon handy. I'm not kidding you. This is how bad it was. And on our breadboard, when the digital circuit would be powered up, we'd have to spray it with Freon while it was running to keep it cool enough so that it wouldn't basically short circuit out. So that's my contribution to, yeah, this is just like not, it's so slow. I don't know what to do here. I'd like to just like throw it against the wall. Won't help. Okay, can this be simplified, Annie? Yes or no?
Yes.
Sure it can, because the last two terms you can factor out of 36 and go ahead and, oh man, is there something I can do here? It's really slow. You have it when your camera is on or too long. I don't think the camera has anything to do. It's not cool, whatever. How many fans do I have on here? No, I got it at maximum. Sorry. Okay. So what is this, after a trig identity, what is underneath the radical? Somebody tell me quick. Before my microphone. The square root of what?
41.
I don't think it's 41. Be careful. What's 4 plus 36 times 1?
40.
4 plus 36 times 1. I know what I'm going to do. I'm going to get off the internet. Maybe that's making it hard. I don't know. Get off of that. Get off of that. Let's get off of here. Huh. Can't seem to get out of here. Leave site. Oh. Did I mention that I hate Google too? Man, those guys are a monopoly. Okay. My battery's low. Okay, I'll check. That could be another reason. You got a point. Well, I'm supposedly plugged in, but, you know, hold on a second. I could be wrong. No, it's plugged in. I'll check it. I'll make sure it's really in there. Okay, does that help? I don't know. Usually it gives me a message when the battery's low, like, your battery's about to die. Okay, so this is 4 plus 36, which is square root of 40, and this is where I do want you to keep going with your radical. I'm not okay with square root of 40. I'll mark you 1 point off. Well, how come? Because you can simplify that radical a little bit because one of the perfect square factors in there is 4, and you can rewrite it as 2 square root of 10. Okay, now what? Good news, this is the super easy arc length problem. So little s is how we denote arc length in mathematics, and they told us that the interval is 0 to 2 pi. And we got that in this case, our speed was just 2 square root of 10, and you're going to integrate that with respect to time t, and that's just going to be 2 square root of 10 t, where t goes from 0 to 2 pi, and I'm writing like 10 times faster than this crappy Microsoft Surface Pro can keep up with me. And your final answer is 4 pi as square root of 10. Okay, and I'm done with that problem. Will I probably give you something like that easy on a midterm? Oh, no way. I don't give something that easy. Why? I like to see if you can integrate or not. I'm really into checking to see the integration skills of my Calc 3 students. So if you took your quiz this week, you probably noticed that I put a lot of interesting integration problems on there where you had to work a little bit. That's because that's how I roll. And I'm preparing you for multivariable calculus when we have to do double and triple integrals. So this is a really hard problem, but not that bad, but it involves the product rule. And if you took quiz 3, you know I love the product rule. I love it. Like, it's super important in mathematics. And so is it going to be expected to show up again on a future exam or quiz? Oh, yeah, because it's important. So I hope you get that when you find the derivative of this vector valued function here, well, this first term doesn't need no stinking product rule. You just go, okay, that's cos. But the second term does. Now what I'm going to do is I'm going to change this to plus a negative. So negative t is going to be my f, and cosine will be my g. And that way, when I go f prime g plus g prime f, I will be fine. So plus, so f prime, the derivative of negative t is -1. There's your f prime. You're going to multiply that with your g. There's cos. Plus g prime. The derivative of cos is negative sine. And you multiply that with your f, but that's negative t. And we'll clean this up in a little bit. Let's keep going. The second term, you're going to end up using the product rule again on the second term, but the first term is just going to have a derivative of minus sine. Plus, and then you'll go f prime g plus g prime f on that t sine t. And I get simply 1 times sine t, there's f prime g, plus g prime, so the derivative of sine is cos, times t. And then comma, and as the very last component, he's easy, the derivative of t squared is just 2t. So there's our prime. Now, is there anything that we can do to clean this up? I hope you notice that these first two terms add up to 0, so they're gone. And that's nice. So the first term, and a negative times a negative is a positive. So the first term in this velocity vector is just t sine t, fine. And then similarly in the second component, voila, the first two terms add to 0, and we just get t cos, fine. Then what? We get 2t. So now we're going to set up the arc length. So arc length is the integral going from a to b, in this case 0 to pi halves, speed. If it's not one thing, it's another. And so when I do the square root, woo! Come on, Microsoft Surface Pro, please.
It's all right during tests to find the magnitude separately from the integral and then.
Well, yeah, you can do it in steps. As long as you're making a legitimate mathematical argument and I can follow it, of course it's going to be okay. It's just when it's a crappy mathematical argument and I can't figure out what you're doing, but magically you got the answer. Like, I'll give you an example. The other day for my Calculus 2 students, they had this for one of the integrals, and you need to use change of variables. So you have to do a lot before you can rewrite the integral in terms of u. And a lot of them would put some like, oh, u is this, and then boom, magically they were able to come up with rewriting the integral, and magically they got the answer, and magically, you know, it's like, really? A lot of magic occurred there. There was enough missing steps where, you know, once they got to a certain point, I could follow what they were doing. But because they lacked the ability to show me legitimately how they got from choosing a u to rewriting the integral, I gave them 0 points. And I'm going to do the same for you. As long as I can figure out what you're doing on your uploaded handwritten work, I'm okay with it. But if you start skipping, I had one kid on the Calc 2. Oh God, this was hilarious. He got a couple problems perfectly right, but on the handwritten, and I gave him 0 points because this is what he wrote on both of them. I don't think I need to show you the work because I saw these problems on the homeworks in my math lab and I was able to do them perfectly.
That's what he wrote.
Yeah, I actually wrote that. And I'm like, dude, that's interesting. Thanks for the tip. But 0. You know, you don't just write, yeah, I know how to do this, trust me. Oh, God, he should be an attorney or a politician or both. So look, don't do that. So these two terms here have a common factor of t squared. So if I pull out their common factor and then I use a trig identity, that's going to be nice. Now this guy doesn't go away because he's going to be 4t squared, but I claim that these are going to be like terms because the first term, you know, you got this, you know, 1 times t squared. Okay, fine. And then what's t squared plus 4t squared? Quick.
5t squared.
Very good. And then, Adriana, this is where I'm talking to you. I think you were thinking about absolute value here, and you are going to use that if you have a product under your radical. And so this is going to be, if I simplify, square root of phi of absolute value of t dt. But I can safely take the absolute value bars off and just call it t, because if you graph absolute value of t and you look at the interval from 0 to pi halves, that interval, the function is just positive t. So you can safely rewrite this integral without the absolute value, since it's on an interval where absolute value is just serving the role of just t. And then this is super easy to integrate. And you're just going to plug in your limits, which are weird. And then your final answer is going to be, oh my goodness, square root of 5 pi squared over 8. Ooh, interesting. That's the exact answer. And when you do an arc length problem, please be sure that your final result is a positive number, because you can't have 0 or negative arc length. Okay, it just is not going to happen. Okay. It might mean that you accidentally tried to set up your arc length integral on an interval that I told you has a sharp corner or a cusp. That's a lot of times how you get 0. I've accidentally done that. Like I was trying to create a calculus 3 exam. This is like 15 years ago. And I always like to do my solution keys before I give it to a student, just in case weird things like this happen. And when I was doing the solution key, I kept getting a 0. And the curve clearly didn't have a 0 arc length. It was kind of a cool curve because it had, it looked kind of like a diamond. And the problem was find the arc length of that diamond. And I was doing something silly. I accidentally was trying to apply the arc length formula on this entire diamond. And I kept getting 0 for the answer. I'm like, dang it, this arc length is not 0. Well, obviously, I hope you can tell there's 4 corners or 4 cusps. And of course, I couldn't use the arc length formula. Oh, don't be me. And so, well, how do you find this guy's arc length? Well, simple. You just divide and conquer. And that's when I finally realized, after I kept running into the brick wall, I just find the interval for one of these little curves and use symmetry and multiply by 4, and then I could have gotten the arc length for that whole shebang. Okay, so have to be careful that you don't do something silly and try to use the arc length formula on a bad interval. Okay? Any questions? I'll take a pause there. I know it's been crazy with laptop problems.
How is it that we'll find one of those cusp points again? Or we'll be going over that?
Are we going to go over what?
How to find a point on the cusp, or the cusp point?
No, I'm not going to go over that. Because it's just, you're going to just, that would be just finding where the velocity vector was 0. The 0 vector.
Oh.
That's all. It's where it's not smooth. So I'm not going to do any problems like that, but you certainly could. You could go get your velocity vector and set it equal to the 0 vector and figure out what times, if any, because some curves don't have any sharp corners. Shoot, you could have, you know, that helix we were looking at that kind of looks like a coil or a spring. Helixes, woo, don't have any sharp corners. In other words, their velocity vector is never equal to the 0 vector. It's always beautiful and continuous velocity vector. Okay, so that would be the way you would do it, and I'm not going to go there. Now, when I used to teach this class, and we used to have a 17-week semester, which we don't have the luxury of anymore, I used to teach, go find the time values at which the vector valued function has a cusp or a sharp corner. And all it is, again, is you find the velocity vector set it equal to the 0 vector and find the time or times, there may be more than one, that make the velocity vector the 0 vector. Okay, now let's do the arc length function real quick. And this is kind of cool because I think I mentioned more than once this, you've been with me for a month now, that when you get like parametric equations for a line, which you could just throw into a vector valued function, those parametric equations are not unique. Like you could give me a different answer as long as, you know, you can't give me any answer, but you could give me a different answer which would be just as valid for representing that line. And the same goes for curves. Curve parameterizations via vector valued functions are not unique. Now, a common parameter is time t. That's a common parameter when you're parameterizing a curve. But it isn't the only one. There are other ways to parameterize a curve. So one way is using this thing called the arc length parameter. So, I'm just talking you through what I'm saying here. So take a look at this twisted cubic. That's kind of a cool curve. It kind of looks like one of those helix guys. But I claim that these two are equivalent. So you're like, well, really? Although this one will sketch out between its parameter going from 1 to 2, and this one where the parameter is u instead of t, as long as the range is 0 to ln of t, those two curves will match up perfectly, okay? Now, when you're, if you're going to graph one of these curves, and I think this is where I like to call up my, like I want to show you the twisted cubic if I can. Let's just see if I can do this because it's kind of fun graphing in 3D. So when I'm using my new calc, I don't know how to do this in GeoGebra. I'm sure you can find out. I'm sure you have a Google up a how-to thing. And there's so much software out there. But if I were to give this vector these components, t squared, and then the cubic here, that's why they call it a twisted cubic, t cubed. And I got to check my parameters because sometimes this software limits my x's, y's, and t's. Here it's limiting the t. I'd like it to go from, let's have t be, or is that t? No, t is down here, 0 to 1. How about negative 20 to positive 20? Let's just see if that does it. I might have to change the x, y, and z. Yeah, it's only showing you a portion of it. Let's change, let's try this. Negative 30, 30, negative 30. I'm just changing my range here to see if it'll draw a little bit more of the curve so it'll be more fun. Now, I'm not going to ask you to try to draw one of these puppies, okay, in 3D. Okay, don't worry. Like, oh no, she's going to ask. But you might want to have some knowledge of it. Whoa, that thing is like way out there. So if I try to rotate it. Whoa. Doesn't that look kind of cool? I don't know if you can see what's going on there, but it's... so if I try to draw it on my paper, whoa. This twisted cubic, yikes. So go back to where we're at here. So a cubic, yeah, it keeps telling me my battery is low. And that must be the problem of why I'm having this problem. But here's the thing, I don't know. I guess my plug is like messed up. Let me just see something here. I got all these extension cords everywhere. It's pretty much a nightmare. Okay, I think it's plugged in now. I don't know. Let's try that. Hard to say. Too many wires in here. Okay, so my battery is going to die soon. The outlet may not be working. All of these could be true, people. Here's the thing. I'd like to be able to go back to my office, but and so I may end up Zooming from my office. But then my boss told me that the internet on campus sucks too. So I may be, you know, I don't know. It's going to be worse. okay? So I hope you guys remember that y equals x cubed looks like, it looks like this, if you ever graph y equals x cubed. And so the twisted cubic in 3D is kind of cool because it's got sort of that, sort of a look of the cubic that you know and love from, you know, maybe a pre-calc class. It sort of comes in here and like it sort of has a little twist to it right at the origin. So it's kind of cool. Okay, now the idea here is we're going to come up with a brand new way to parameterize. So how do you parameterize to begin with? Well, I discussed that already. My power is not going out. Thanks for the tip. Everybody's an electrician now. Okay, so the idea is get the arc length function and reparameterize the curve using the arc length. And I write about this in my book, if any of you have bought the book on Amazon, and I go over a few problems, and so if you want even more. So it looks like, this looks like the arc length function itself, except instead of t's, I just replaced the t's with u's, so don't freak out. And the reason why I replaced everything with the letter u is because one of the limits, the upper limit on this integral is a t, so that's why. So this is going to be, and typically this is 0, the lower limit, although it doesn't have to be, but let's just do that for practical purposes. And so you're going to basically do the arc length as speed. So what about parameterizing using the arc length function? If you parameterize using the arc length function, some really cool properties come about. From the fundamental theorem of calculus, if you take the derivative of your arc length with respect to t, it'll just give you this the velocity vector's magnitude, aka the speed. And of course, why is that? Well, you know, when you differentiate an integral, those two operations are inverse operations, so you just get back that. And then here's another cool fact: if your vector value function is parameterized by the arc length and not just any old t, if your speed is equal to a 1, that doesn't always happen. If it does, that means that what? That if you were doing an arc length calculation, and if a were 0, like it typically is, it would just give you back t. So what is this saying in English, in case you didn't get it? If speed equals 1, the
Oh no!
We lost her. It was
Oh
so cringy to
no!
see her dying like this.
We were so close too. It's 9:49. If only there was a minute more of a battery.
Remember, this is still being recorded.
Oh.
It was just so painful to see what's going on.
She's gonna be so pissed.
All right, who's in charge of the meeting now?
okay, so I'm trying a different outlet right now. Can you hear me?
Yeah.
Sorry.
Yes.
Yes.
Either internet problems or computer problems. I'm never free of issues. That's the way it is. Okay, so if your speed is equal to 1, what this means, what does it mean? It means your curve is parameterized using arc length. So that's like a true-false question, okay? Will there be true-false questions on quizzes and exams? Yes. So you want to know how to do them, all right? So it's important. So take a look at this example 6, and I claim we already did this curve from a previous example. We looked at it, and if you recall, we actually did try to find the arc length. So the arc length function is a little bit different from arc length. It's similar though. So you're going to go, okay, here's the definition where you have the speed, but you have the variable of integration be used because one of the limits is t. You can't have that match. And if we just use the traditional lower limit of 0, and we ended up getting 2 square root of 10 du here, this is ending up being 2 square root of 10 u, where u goes from 0 to t, and then you'll just get 2 square root of 10 t. So what are we saying? The arc length function is essentially, and your answer, if you will, is s, the arc length, is the same as 2 square root of 10 t. And that's going to be your trick, because over here in part B, you're going to re-parameterize your curve using the arc length s as your parameter. Okay, fine. So what you're going to do is you're going to solve for t with this little equation you have now, but t is going to be s over 2 square root of 10, and then you're going to substitute this into your vector valued function. Everywhere you see the letter t, you'll replace it with this quotient s over 2 square root of 10. And so r will now be reparameterized using s instead of t. And so everywhere you see the letter t there, you're just going to go, I'll replace it with s over 2 square root of 10. And you may want to reduce a little bit because these 2's cancel here and these 2's cancel, so you make it look pretty. And there you go, you're done. I claim that if you graph either of these, like in your, in my graphing software, I could use either of these. It would give me the same curve. It may sketch it out over a different period of time. The ranges may not match, but it's the same curve. Now, another cool property is if you do have your curve parameterized using the arc length, it'll always have the speed be equal to 1. So your r prime for this particular curve that we just got, I'm just going to take the derivatives of each and every one of these components, and I'm just going to simplify a little bit. Now, folks, why is it kind of cool to know how to reparameterize something? Because then you can describe a curve in a different way. My master's thesis many years ago, my master's thesis was really weird because I had to parameterize a fractal. And fractals have infinity arc length. That's right, infinity arc length. So I had to parameterize it in a really weird way. Kind of like computer science, where I cut it up into halves and halves and halves, and it was fun. So if you take the square root of the sum of the squares of all of these components here, we're getting somewhere, and then you try to simplify that radical somewhat, you're going to get the square root of 1/10 plus, and then these two terms here have a common factor of 9/10, and if you factor out the cos squared plus the sine squared and use your little trig identity that says, hey, that's going to be a 1, you'll get 1/10 plus 9/10, but that's 10/10, and you have the square root of 1, which is 1. So hey, the speed is 1 like it should. So why do you care about doing this? One of the things that's kind of neat is you can tell where you are on the curve if you've traveled an arc length of s along the curve. So this will be a similar problem on your My Math Life homework. So take a look at this. You'll know how to do it. So we already did this. We got s is equal to 2 square root of 10t. We did this already for part D. So they're asking us, what if your distance is pi square root of 10/3? Where are you on the curve? Well, they're basically telling you that this is a distance, which is arc length. So you're basically taking this formula and substituting in place of the left-hand side the arc length, how much distance you've moved on the curve, and that has to match 2 square root of 10t. You solve this for time t, and that's pretty easy. You just divide both sides by 2 square root of 10, and then reduce, and I get t is equal to, after reducing, pi 6, and then you substitute this into your position function, which is the original vector valued curve. So r evaluated at pi 6 is, so if you look at the curve 2t, that's 2 times pi 6, and then 3 sine 2 times pi 6, like that, and then 3 times cos 2 times pi 6, and then where the heck is that? That's going to give you a point on the curve, the position, and so you're going to get a weird position here, pi thirds, and I think sine of pi thirds is what? Square root of 3 halves?
Yeah.
And then cosine of pi thirds after reducing is a half. And so after reducing those, you'll get this position on the curve. So that's kind of cool. Now, true or false, and this is where I mentioned, hey, we're going to do true or false. The curve t squared, 3t squared, is it parameterized by arc length? Yes or no? And the quick and dirty way to answer, I mean, you could go find the arc length function and plug it all back in and see if it matches, but the quick way is speed equal to 1? And if it is, then the answer is true. If not, it isn't. So if you go get your speed, and you go, is that going to be equal to 1? I don't know, let's find out. And so when I take the square root of the sum of the squares of these components, I don't get a 1. I get some scalar function of time t. I get something like 1 plus square root of 1 plus 4t squared plus 36t squared. And that certainly is not equal to 1. So forget that, it's false. And that's good enough for government work, okay? I think this is a good place to quit. Let me just mention what we're going to do on Friday. We're going to look at how to find arc length, curvature of a curve. And there are actually formulas to determine how curvy a curve is. So if you're going to be a civil engineer, you want to care about this. Why? Because, you know, if you're building some freeway ramp, you may not want it to be, you know, too curvy because it might be hard to maneuver around. So there are ways to measure how curvy a curve is. So we're going to look at that next time, and then we'll also look at the idea of acceleration always existing in a plane containing the tangent and the unit normal vectors. Okay, so I'm done. I'll stick around for like 5 minutes to answer any last minute questions. I'm going to stop the recording. We are officially done with today's lecture. Woohoo! And I also have office hours.